There is no one.
No one?
I don't think so. There's only one participant that's us, I think. Ah, there you go. You think this will be readable?
Can you write something?
Think so. There is a line. I see a line there.
Yes, I can read. A equals to B.
Because first time we did this and when I was looking at it, I couldn't read it. So, okay, up to you guys.
So you can ask Professor Niranjan.
Niranjan, is this readable?
Yes.
A equal to B?
Yep.
Yes. So we'll keep it this way. Yeah. There's a line there, but it's fine.
Oh,
It's on the wall. On the wall?
yeah, it's on the wall. So 2 weeks from this Friday, we have an exam. Yeah. On any general questions? How is it anything that I should do that's different? In class or in class, probably. What on everything that we do until that day, including a Monday. How many questions and how much time?
Usually it is about 4 to 5 questions. And it is 75 minutes, one period. That's how it is. Sometimes I have done take-home exams, like take-home in the sense 3 of the questions is take-home, and then bring it back, and 2 of them is here. But as of now, I think it's going to be all exam in the class. Expect small parts of the homework questions, like not exactly, but when you're doing a homework question, there are lots of parts that comes in, and there is a lot of input that goes into it, which is reasonably straightforward, one would think. But I can ask just one piece out of it. Like what is gradient of some function, and make it slightly interesting. That's all. If it is physically related, that is what I try to do. Okay, does that help? So 5 questions, expect 5 questions. And each one expect about, you should be able to do that in 10 to 15 minutes. Look up old exams, that's a good way to see it. If sometimes what happens is that old exams have take home part to it, which is long. Take home part will be exactly like a homework. So since some of you are taking the course with me for the first time, and I don't know you guys very well, so I'm going to make it a full proper exam. And then if I realize that okay, everything is going fine, then I will change it to take home or something. And sometimes I give the option that do you want to make it in the evenings? The exam should be make it in the evening or not. But as of now, I don't see the purpose. I think for the last few years, it has been consistently in the classroom. So I'm going to keep it in the classroom 75 minutes. And let's see. You have a class right after this. So 75 minutes becomes a deadline. Unless you want to come early. That was that sometimes people have done this. instead of starting at 9:30, we can start it at 9 o'clock or even 8:30 if you want. Think about it and come back to me. You have to discuss among yourself. And again, the exam will be possible to do it in 75 minutes, but if you really want more time, it cannot hurt. So I can make it earlier, let's say 9 o'clock or something. Start helps you with the time. That's okay. And people can start at 9:30 also, but then you cannot go out and half an hour. So, yeah, think and tell me. Okay. We started working with basis vectors. Basically, it's broadly called curvilinear coordinates, like we are working in cylindrical coordinates, spherical coordinates, and so on. So how do we develop the basis vectors, the unit vectors, and what are the things you can build out of it? So here we will talk about what is called a connection. That's a broad terminology, but if you're familiar with relativity, then you also call it Christoffel symbols. That's it's basically how unit vectors change with position. As an idea, we know this, like a unit vector which is radial, as you rotate, its direction changes. Right? That's the basic concept, but we want to quantify. We want to really construct a quantity that has this information that it is actually changing. Right? So that's the basic idea, and I will talk about some related constructs in that. And so let's think of what we have done as of now. So we talked about tangent vectors, tangent basis vectors, maybe. They're also called covariant basis vectors. In general, we have been labeling it E vector, E with a subscript I. If we are in 3 dimensions, it is that readable? I
Yeah,
cannot read it. I'm old though.
now it's readable.
Niranjan?
A little blurry.
Little blurry, okay. Yeah, that's what I would expect.
It looks better, but still blurry. I don't know why.
Zoom in? No? So we should confine our board to this one, if this was better, right?
Mm.
I think when you write the equations, it should be fine.
But I cannot read it, so. How can I?
Oh.
So this is because we moved it, that's it. Hmm? Oh, yeah, maybe I can start from here, right? Yeah. Good.
Yeah, that area is clear.
Let's start from here. So. So, is this better? I should write bigger.
Yeah,
Tangent, is that readable?
Yeah, I can read it.
Without studying, right? Okay. Tangent. Yes. I might naturally decrease the size, it is just my tendency, but then ask me to make it bigger and I'll make it bigger, so. Happy to. Okay, E. I, that was thought of as if you have a position vector, find the change in position vector with respect to a coordinate. So this is a change in position vector with respect to the coordinates ui. The ui, so this is change in r with respect to U of I. And U of I are the actual coordinates here. With respect to coordinates here. That's a definition. And you have normal basis vectors. Steps, so it's in the superscript, and that's simply the gradient of the coordinates. This is the change in U of I with respect to R. Like that's a, or you can say gradient of, it's good to have an example. That's what we did last time. You have the coordinates that you can use to coordinatize space, circles. One more. And half lines. The half lines. These are circles and half line. By half line, I mean start from the origin and go all the way to infinity. So U of 1 in this case is rho, the cylindrical coordinates, and U of 2 is the angle phi. If you want to represent a half line, you will use the slope of the line, or not the slope, the angle that corresponds to the slope of the line is used to characterize that, describe that line. And those are the two. And if you want to stay in 3 dimensions, you can keep the third one as Z itself. That's your cylindrical, you would say cylindrical polar coordinates. And we showed, we derived last time that E1 is equal to, it is rho hat, and remind me. E1 is just, yeah, E1 is rho hat itself, right? So that's rho hat itself. E2 is pi hat multiplied by rho multiplied by pi hat, and E3 is Z hat in the direction of the normal vectors are rho hat, Q is pi hat over rho, and 3 is Z. That's your basic construct that you define these two, and then and as an example for cylindrical polar coordinates, we calculated the two basis vectors. Now, when we do this, there's a advantage that by construction, the way they are constructed, the way they are defined, it turns out that they are always orthogonal. And not only orthogonal, they come out to be orthonormal, orthonormality. Orthogonal means they are perpendicular to each other, and normalized means that when you multiply the two vectors, you get a 1. Right, that's the idea. So orthonormality relation is that, and the only difference is that you pick one vector from here and the other vector from here. So it's not that if you multiply, for example, E2 dotted with, so if you multiply E2 dotted with E2, that's equal to rho squared. That's not normalized. But if you pick one from here and one is a tangent vector and one is a normal vector, they come out to be normalized, and they can be put together and written in a nice way. So that's I
got it. If J is equal to delta ij. That means that it is, unless I is equal to j, it is 0. That means it's off. It is good to think of what kind of quantity these are. Like, for example, we have been talking about scalar, vector, tensor, and so on. So I can ask, is this a scalar or a vector or a tensor? It seems like it's a vector because it's only one index, right? But notice there is another vector sign on top of it. Like, so in the notation that I have developed, remember earlier we said there is a dyadic and there is an index notation. This is a mixed notation. So for each unit vector, there is a vector, right? For E1 equal to 1, that's a vector. 2, that's a vector. 3, that's a vector. So if you combine all these three, so this is actually a tensor of rank 2. One of the indexes is represented as a vector itself, and the other one as I. Ideally, if you were to, once you get very comfortable with this and you have a good insight of all this, then you would say this is ij. Right? There are two indices in it, but this is for convenience. There is more insight in this when you think of this as a vector or that's a gradient of a coordinate. So it's just to get some physical insight of what gradient means that you actually split this into two. So this is actually a tensor of rank 2. One of the indices is in the explicit vector sign, and the other index is in the actual index. So what would this be then? So this was a tensor of rank 2. That's a tensor of rank 2. On the left hand side, is that a rank 2, rank 3, rank 4? What's the rank of this tensor, or is it a scalar? The dot product here. Sufficient here. Is this a scalar? No, yeah. So is it a vector?
I think so.
How many free indices does it have?
Two.
Again, yes. Louder, clearer. Two, right? So it's a tensor of rank 2. And the dot product here is dotting the two vectors. If I do not put the dot product, so let's say this quantity here. What is this? This is a scalar tensor, if vector tensor, if it's a tensor of what rank? Four, correct? I, J, and there is an index which I am not explicitly writing. There is an index which I am not explicitly writing. So 4, 2 of them contract to give you this. Okay, one should start getting a feel for what's going on. So these are the kind of notations you're building, which is kind of half built notation. Half of it is explicitly written, half of it is written in vectors, but it has advantages on it. So this is the 4th rank tensor. When you dot it, 2 of them gone, so it's 2, and on the right side they will be balanced, right? Always the indices have to be balanced on the right and the left. On the right side there are 2 indices, so on the left also there should be 2 indices, and so it's a tensor of rank 2. Let's do also completeness relation after this. And completeness relation, notice how this changes. There is E. I write upside, it doesn't really mean much. I mean, I can write it up or down, it doesn't matter. So, and there is E. How many free indices on this? One, two, three. 3. How many says 0? Let's dig into that. Is it a scalar? That's what it means. It's not a scalar. Is it a vector? That means there should be one free index. Remember, if it is repeated, it's not free. So I is repeated. That's not a free index. So after you get rid of I, there are how many more remaining? Remember, some of them are being written as vectors. So there are 2 vector signs here. So there are 2 free indices there, which is not being explicitly written. So there are 2 free indices, 1 dummy index. So in principle, 2 free indices, which should balance here. And that, since it is written as a vector, it's being written here. So that's the 2 free indices, which is not explicitly written, it is written as a vector.
So if it's not written, we can say that those are free.
Not if there is a, for example, this is not written, there is a vector here, right? But there is a dot product. The dot product practically means, remember, A dotted with B
It's a scalar.
is a scalar, and this is also AI, BI. Right? So if I were to write this as an index, I will say this is a K, that's a K, which is summed over. So it is there, but it is summed over. So it's not a free index. Here, there is no dot product. So this will be a K, this will be an M, that will be an N. It will be 2 different indices. Is that clear? Correct. And there's nothing, and if you do, for example, if you were to do this as a tensor analysis, so subject, then you will write index there. It's common to write index. But sometimes when you write it as vectors, then you can see that, oh, this is a gradient of this, so that you can have a physics associated with gradient. So most of the physicists will try to do it, mix up this notation. But there's nothing wrong in writing this as an index itself, and that's what it is. Sometimes it is useful. As far as algebra goes, it's easier. Insight is lost, but algebraically, it's easier to maintain them. Okay, helps. And so that's a 1. Now, orthogonality, all of us probably have a clear understanding of. It is basically the normal orthogonality. What does completeness relation mean? You've seen this in quantum mechanics. If you've done quantum mechanics in some form before, this or always you say this is a basis vector, or there you say it's a vector space or Hilbert space, which is complete. And often we don't talk too much about it, but it's important in this. So in whatever form you have, what do you understand by completeness relation? Anything that comes to mind?
So every basis has its reciprocal.
Yeah. But that's not a statement of complete. That's more of orthonormality in the sense. This is your basis, that's your reciprocal basis. And if you pick one vector from the normal basis, the other from reciprocal basis, they will always come out orthogonal. So that's the advantage of it. Like if you're doing crystallography, for example, the lattice will be like this. So let's say this is. It's very easy to have a crystal structure with this as your lattice, and they are not perpendicular to each other. They're not orthonormal by construction. So you would think that, oh, that's too much work now if you have to work with a non-orthogonal system. But then that's your unit vector. So this is your E1. And that's your E2. But now you build a new system, which is called a reciprocal basis. And that will be your E2. This will come out to be, let's say, this will be your E1. Using cross product to do this. So this is E1. And this will be your E2, I suppose. E1, yes. You check if this will really come out. There's a homework problem you do associated with this if you've opened your homework. And let's see, E1 dotted with, no, this cannot be correct. So this is EQ. Yeah, this is EQ. That's one. It's and now you can see that E1 dotted with E2 is perpendicular to E2 dotted with E1 is perpendicular. So by construction, it comes out to be perpendicular. Okay, so you will see this in your homework where I just did it in my head and didn't provide any kind of it's a mistake. Check it with homework. Is that clear what I? So basically, one of the vectors from the basis vectors, the other from the reciprocal basis, they will always be perpendicular by construction. Like you don't have to do anything, it will always come out to be perpendicular. So that's the advantage. And that's slow. But yeah, we're talking about completeness relation. Completeness relation, often you will state it in the following way. If you have a space, two-dimensional space, give me any two vectors. I can write every other vector as a linear combination of these two vectors. It doesn't have to be orthogonal. Okay, so for example, give me any vector. So let's say this is A, and that's your B. And any vector can be written as a linear combination. That means alpha times A plus beta times B. For example, if I want to write this is my vector A, how many pieces does it have of A? I'll take the projection of this. This is alpha here. That's alpha. And then project it along B. It's this one. Project it along B. And that's your beta. And that's beta, that's your alpha. So any vector in this way can be written in terms of two independent vectors. So first I just said two vectors. Now I added a small t, said two independent vectors. By independent vectors means if both the vectors are in the same direction, then obviously you cannot do this. Because then the other vector is not there. The first vector is nothing but the first vector itself multiplied scale vector. So that's you need at least two vectors in a plane. And you can always do this. This is a simple statement of completeness relation. That these A and B are complete in the sense that every vector can be written in terms of. So now this is a geometric way of doing it, but I say this one has that feature, this completeness relation has that feature. So how do we see that? So let's see completeness relation in action, let's say. So this is any two vectors, think of cylindrical coordinates if you want, or if you want rectangular coordinates. Let's say we have a vector A. As I said, unless I give you the basis vectors or the coordinates, this necessarily does not specify which basis I'm using. This is just a geometric idea. It has a length and it has a direction associated with that. And if I want to get the components in a basis vector, what I do is I use a simple idea that A dotted with 1 is A itself, right? That should be very straightforward. But now, at this stage, specify your coordinates. Whether you're in rectangular coordinates or cylindrical coordinates, either way, let's say we are in cylindrical coordinates. So that's A dotted with cylindrical coordinates, let's say this is E1 is rho hat and so on. So this will be completeness relation. One is E I. Call this, define this to be AI. Which is something, but if I were to explicitly write this, it is A1, E1 plus A2, E2 plus A3, E3. Or AI is equal to A dotted EI. You would say this is a projection of A along E. That's our understanding, right? If I have a vector A, often because we are trained so much in rectangular coordinates, we think of a vector like this. This is our intuitive feel for a vector. But it should come the other way. This is the geometric piece, and this is a coordinate representation of a vector, where A1, A2, A3 are the components of the vector in the basis vector of E1, E2, and E3. Any questions on that? It's very straightforward. The same idea as here. Now I have given some meaning to alpha and beta in terms of completeness relation. So since they are complete, they should, any vector can be written in terms of this, and I can pull out the three components. That's what we say it is the direction cosines of the vector. If we have such a basis, that could be more, as I said, it could be more than one basis. There is nothing special about cylindrical coordinates or spherical coordinates, or if you are in quantum mechanics, you will say this is the position basis or the momentum basis, right? So different bases can be used for that. So let's try to do that and see what we get. It should change, right? Okay. Now, I said A is equal to A dotted with 1, repeating in a sense, whatever I wrote there. This is the same as A dotted with E I. And that's equal to 1 I. Projection of A along. I didn't have to do this coordinate system. Let me think of a new coordinate system. I would have done the same thing, dotted with 1, but this time at a different coordinate system. That's GI. So now it's pretty much like your rectangular coordinates and cylindrical coordinates. So these are components of A along G. So let me call that A bar by G. Immediately you ask, oh, if that's the case, I would like to know how are these components related to AI. That's what you usually do when you rotate a coordinate system. How is the vector components in the rotated system related to the original system? So that's something standard that we do. So we can ask, how is the new components related to the old components? And that's what is called a transformation method. And this is a word from quantum mechanics. Transformation measures. How do we go about that? Let's start from here again. This is, let me write these two. So A, vector A, since there is a 1 I can multiply. This is A, after that I, and I have I. Let me put this in parentheses. This is also A, I. Is the I here free by any chance? Is I free index? Or maybe I should ask, how many free indices in this quantity? The quantity I'm pointing. Zero, no, just three. Three. I is repeated. So if you think of it, so let me write this again so that I can at least show you how I'm doing this. So that is EI, right? So if I were to count, that is 1, 2, 3, 4, 5. There are 5 indices that is coming. 2 are explicit in the say I, and 3 are coming as vector signs. So there are 5 in total, but I is repeated. So that's dummy, it's not free. So it is 5 minus 2 immediately, so that's 3. But these two are dotted. There is a dot product, which is the same as being dummy. A dot product has a AI representation. So again, subtract 2. That's 3 minus 2. So that's 3 minus 2 is equal to 1. So there's only one free index, and that is in the form of a vector sign. If you notice on the left hand side, there is only a vector sign showing up. Remember, always indices match in an equal sign. So if I ask you how many free indices there is, you can be clever. Go to the left side. Don't worry about all this. And here there is only one vector sign, so there's only one index. It must be true that this is, otherwise this equation is not correct. So that's another way of doing it. Either way, these are the components of the vector in the basis vector of E. These are the components of the vector in the basis vector of G. And you might want to find the components of one in terms of the other. So how you can do that is, I want to get the relation between this and this. So you would like to get rid of, so whenever you have vector signs, you want to use orthogonality, right? So you want to get rid of E. Whenever you want to get rid of the vector E, you will use orthonormality. Again, in quantum mechanics, this is a trick that you use. Whenever you want to bring in a basis vector, you will use completeness relation. Notice I use the completeness relation to bring the basis dependence. Whenever I want to remove the basis dependence, I use orthogonality. So that's a standard trick you will use all through. And in quantum mechanics, you kind of intuitively do it because you do the algebra again and again there. But the basic idea is this, that whenever you want to get the components, you use completeness, and whenever you want to get rid of the basis vectors, then you will use orthogonality. So now, if I want to use orthogonality, I can either use this or here. So let me try to use orthogonality in EI. This will be A dotted with EI. That's the components of the vector in the basis vector of E. And I want to use orthogonality, so dotted with EJ. Let's see, I cannot use I again. So it's A. So I will do the same thing on the right side. EI dotted with EJ. What is this box quantity equal to?
Del Ij. Del Ij.
Del Ij, right? Orthogonality. Very good. Like you're taking a dot product between the three basis vectors, and one is a tangent and one is a normal. So that's it. That orthogonality gives you del Ij, and del Ij multiplied by this gives you J, right? So this is A dot with I, which is now becoming J, right? Is equal to A with GI, which is the projection in the other part. And this is your, again, maybe I should ask this quantity here alone, so the one that I'm marking, how many free indices? Good. 1, 2, 3, 4, but this is dotted, so 2 gone, so there's 2 remaining. It's a tensor of rank 2, which means it's a matrix. You think of it as a matrix, so let me write that as T I J. Let me for a moment write this explicitly. That's G I dotted with E. That's a transformation matrix, so let me write that. So this I said was AI. Components of the vector A in the basis vector of E. A projection of this vector along the basis vector of E. This is equal. This one was A bar. Right? And this one, let me call this T I J. That's my transformation matrix. If I want the projection of one vector in terms of another basis, this is how they will be related. Then last, this one? Oh, this one? This one. Oh, this is J, but that's because what's been wrong? Oh, yeah, this is correct, J. Because that's free, right? Is that what you were also pointing out? Yeah, very good. And it should be the case because on the right side, I is dummy. So J is free, the left side also should be free. So good point, very good point. I think that's caught it immediately. So that's good, very good. Okay. We should be able to see this in rectangular coordinates, like cylindrical coordinates and rectangular coordinates, how is this related? So how is the vector related in there? So let's see. What is A1, E1, and so on? What is a vector A in the direction of row hat? Right. So let's say this is a row. So again, maybe not a vector itself, maybe the position vector, or so let's say E1. No, I want upstairs, right? So because I'm going to construct my PIJ. So E1 is row hat, E2 is phi hat by row, and E3 is Z hat. And G1 downstairs, let's say is X hat, G2 is Y hat, and G3 is Z hat. Right, that can be your two independent basis vectors. And you would say, if you have a component of a vector in one basis, the components of a vector in another basis, how are they related? Like usually this is the transformation matrix. If it's a rotation, then it's just cosine theta, sine theta. So let's do this. Tij would be equal to the first one is, so let me write this. This is 1, so this is the no, G1. G1 dotted with E1, 2 dotted with E1, 3 E1, 1, 2, 1, 3, 2, 2.
Excuse me, Dr. Sajes.
Yes. Oh,
Can you-
camera.
The camera,
Good.
thank you.
Yeah. Okay.
Thanks.
So that's your transformation matrix. Again, we will. You should always think of quantum mechanics as this basis vector dependent comes out, and comes out much more explicitly. And you say how is the basis vectors, or how the components or the projections in the position basis related to the momentum. So we look for these quantities there. It means when we talk about that, it can be a dot product in the form of an integer. But what is this equal to in this case? This is equal to G1 dotted with E1, so that's X hat. Dotted with E1, which is rho hat. So this is Y hat. Dotted with rho hat. We have rho hat. X hat dotted with Y hat over rho. Y hat dotted with Y hat over rho. G hat. Keep going, one more step, you can write this equals here, still visible. X hat dotted with rho hat is how much? 0, no? Radial vector in cylinder, I think of this like this, so that's your X hat, let's say. That's your Y hat. And rho hat is somewhere here, right? Think of a circle going, and then phi hat is perpendicular to rho hat. Usually you'll draw a circle and write the rho hat in that direction. So what is X hat multiplied by or dotted with rho hat? So that's phi direction here. So that will be cosine phi, right, in that picture. So this will be cosine phi. X hat dotted with phi hat, so that's cosine of 90 plus phi. That's cosine of 90 plus phi is a minus sine phi. Minus sine phi over rho, and that's 0. And this will be Y hat dotted with rho hat. That will be sine phi. And Y hat dotted with, so this will be phi again. That's sine phi. This is what is called a transformation matrix between the basis vectors of rectangular coordinates and the cylindrical coordinate. Notice, just follow the rules, and it is mostly collecting dot products in a sense, or collecting the components of a quantity in a. And in your homework, this shows up in the last few parts of the problems that I have asked you to do. You have to do this. I have done all this for cylindrical coordinates. It is relatively easier to the spherical coordinates. You do this for the spherical coordinates. Like that's what your homework. Any questions at this stage? Okay, so once we have the idea of transformation matrix there, so let's now talk about the connection, how these quantities change with position. This is broadly called the connection. And sometimes we'll call Berry connection or Christopher symbol. So those are the quantities that you can build out of it. So we have basis vectors, that's EI. That's, I could have picked the tangent basis vector or the normal basis vector, either one. So I chose to use the tangent basis vectors, and I want to talk about how do they change with coordinates. As I move the basis vectors around, how do they change it? And especially if I go around a full circle, do I come back to the same point or not? So those are the questions that are interesting in physics. And for that, the quantity you will build is change, right? Whenever there's a change, you say gradient, like change with respect to position. So that's the quantity that you want to talk about. So this is called the connection. This is the connection. How many indices does it have, or how many free indices, like not the explicit one, how much freedom does it have? 3, right? 1 vector here, 2 vector here, and an explicit index. So let's say this will be a third rank tensor. And if I dot it, then it becomes a single vector. But currently there is no dot product, so these are 3 explicit indices. And if you're familiar, if you're at some popular level seen what is called Christoffel symbol, and it has 3 indices, but we will talk about that in a minute. So we are typically interested in the components of this connection, not necessarily the connection itself, the components in that basis. So the basis we are working with is EI itself. Find the basis along that direction. So it is good to build a quantity. Say, let me see what's the thing that you have in your homework. Yeah, so let's not one left. Let me multiply this. First, take the gradient and then multiply with J. And I take a dot product. This has how many free indices immediately? You should ask. This is 3. This has again 3 because 1, 2, 3, 4, 5. But out of that 5, there is a dot product. So you subtract 2, so there is remaining 3. And those 3 are I, J, and these 2 are dotted. So this is the vector that survives. So it's good to write this as a vector, which is the free one is this, right? And there is an I downstairs, then the J after 1 in the subscript, 1 in the super script. Notice I could have taken any projection, right? I could have taken a projection from the left side. I could have taken a projection from the right side. I could have taken a projection from both sides. And this is called the bend connection when I do it this way. So just as an exercise, in your homework, I don't know whether homework is, some of them are optional, right? I don't have the homework with me. I think some of the homeworks is optional, so there's a chance that this might be an optional homework, but I'll show you how this is done. Let's do one of the components. So let's say a I_j would be equal to, now notice that I'm writing this as a vector. It's each element is a vector, right? So it's 1, 1, a 1, 2, a 1, 3, a 2, 1, a 2, 2. That's not common. Notice each element of this matrix is a vector. But that makes it very easy to handle, because if I don't put it as a vector, then it becomes a 3-dimensional tensor, so it's harder to see through. This is sort of the advantage of having partial vector and partial indices. Let's calculate one of them. So let's say we want to, I think I remember this is non-zero. So let's see how this comes out. A 1, 2. A 1, 2 is, this is how you will do. So that's I is 1, J is 2. So that's gradient of E1 dotted with
second, the second normal vector. If if we are in cylindrical coordinates, this is equal to gradient of this is E1, right? So this is rho hat. And then dotted with E2, which is phi hat, and the rho. At this stage, we have a gradient, so maybe I should say a few things about the gradient vector itself, how the gradient vector looks like in an explicit coordinate system. So let's say gradient vector. How does it look like in rectangular coordinates? That's this, right? And this is probably because you've always seen it in this manner, or this was how it was first time introduced. But what's the gradient in cylindrical coordinate? Does anyone remember? So rho hat probably. Derivative of rho. And phi hat over rho. Yeah. And derivative of phi. And that is a z hat derivative with respect to z. Yeah. Now you don't have to be knowing this if you used this many times, you tend to remember this, but then if you are in a new coordinate system, how is the gradient returned? Like for example, spherical coordinates, how will you write it? Or if I were to tell you there's a spheroidal coordinate which you never worked with before, what is the gradient operator there exactly equal to? And then the construction is, so let's think about it. How would you do that? So gradient operator, let's say with respect to, let's say this is also 1. After the gradient operator. So if I want to project it, right? So this is a projection of this operator in a basis. So I'm projecting it. How do I project things? Using completeness relation. That's the same as 1. So this is equal to EI keep this EI times I dotted gradient operator. I'm interested in the projection operators, so I use EI again. I got it J dotted with I. That's what will bring this out. So that's equal. So this will give me an orthogonality relation, and that's J dotted with. So these are the projections, right? These are the projections of that quantity. So what is that equal to? So basically E1, right? So if you are having your rectangular coordinate, so this is E1 dotted with gradient, so that's equal to rho hat times rho hat times p by rho. And the second one will be E2 dotted with gradient, so that's E2. E2 is phi hat over rho, and then this is p by phi, and the third one will be d by dz in itself. Maybe I should make this better. I think there's a better argument I can give in this case. I can also say gradient, yeah, quiz. I think we don't have a quiz. So quiz.
I will derive this using gradient of u of I. Yeah, or just find out what is E. Yeah, EJ dotted gradient of u of I. So find out this function. Evaluate. That will help you see through this mode and ask the question, why is the gradient operator? How does that give you more insight? Remember, earlier I gave you the gradient operator interpretation as what was the interpretation of a gradient operator? I think we talked about this last time, right? What's the interpretation of a gradient operator? Geometric interpretation of a gradient operator?
How much difference does it have each direction?
Yeah, but we also said there was a normal vector definition, right? If I have temperature in this room, if I have a function, so it's a normal vector for that function of a surface. But if I have a, let's say, I think the idea was if I have f of x, y, z, and if I take the gradient of that, the moment I say this is equal to a constant, that's a surface. F of x, y, z, let's say is equal to 3 is a surface. The gradient of surface is normal to that surface. So this is normal to every point on the surface. But as Aryan was saying, it's also nice to think of this as a change in x direction, change in y direction, change in z direction. But then that becomes a coordinate dependent quantity. I first tell you what is x, y, z. Instead, you can think of a gradient as a derivative in the direction of A. This is, if I put a dot product, then it has a meaning. For example, I dotted the gradient is equal to d by dx. This is the gradient of the change in the function in the direction of I hat. This is the gradient in the direction of A hat. But if I don't have any of this, then I have the normal way. It is that has a more nicer interpretation that it's perpendicular to that circle. But often we are working with the derivative in a particular direction. All that because I wanted to do this derivative, so I wanted to explicitly do that. So let's calculate that. So we said this is rho hat. This is rho hat. D by d rho of. Let me explicitly write the whole thing. That's phi hat 1 by rho d by d phi plus z hat d by dz of rho hat. Relation like this as square brackets. That's your parenthesis, the same parenthesis as you had here. And then after I take the derivatives, I will take the dot product. These derivatives are acting on this vector rho hat. Rho hat is a radial vector. How does it change with the radius itself? Geometrically, can you think it up? These are radial vectors. At every point on the plane, there is a radial vector pointing away from the origin. What's the change in that radial vector with respect to the radius itself? 0, because it doesn't change, correct? So that's a good answer. So you have this. So if I were here, the radial vector is in this direction. If I were here, the radial vector were in this direction. Here, it's here. So if I change the radius from here to here, there is no change in the direction of rho hat. It's only when I change the angle there is a change in direction of rho hat. So this derivative is 0. Okay, so that's equal to 0. You can explicitly see this. You can also explicitly do this. We try to do that also. So we are talking about derivative of rho with rho hat. I'm saying geometrically that is 0, but if you're not comfortable about that, do this explicitly. D by d rho hat is cosine of phi in the I hat direction plus sine of phi. This is the algebraic way of doing this. There is no rho dependence in this, so that's 0, that is 0, that is 0. So that's an explicit algebraic way of doing it, or a geometric way of doing it. So this is geometric, the second equality is algebraic. Let's do the other one. There is a d by d phi of rho hat. What is that equal to? Phi hat is, rho hat is here. How does it change when I change the angle? How does my radial vector change when I change my angle? It's like saying if you're doing centric, when you're going in a circle, how does your velocity change as you go around, right? It changes direction. Let's say it's going uniformly, it changes direction, the speed remains the same. But how does it change? What is the magnitude of the change? This is equal to, yeah, good. Yes, you said 5. 5 hat. So if you do this in physics, like you say you're going in a circle, all done this, it's just in a different context we're talking about. So that's your position R. Right? That's your R. And your velocity is derivative with respect to time. So R is equal to magnitude R times the vector R. So let me say it is going along a uniform circle or on a circle, so its radius is 8, it's fixed. Like that's how you would change R hat. R hat. Or in this case, this rho hat. Sorry. This is rho hat. This is a particle going in a circle of radius 8. Position of the particle is on a circle, radius a. That's a vector. Velocity is derivative of position with respect to time. A is fixed, so it is a times d by dt of rho hat. And you would say, oh, how does rho hat change with time? You would say rho hat is this, or geometrically speaking, you would say that R is changing, right? This is R is in the direction of rho. That's changing. The change is in this direction. In your physics textbook, you draw this diagram and you say that it is tangent, but then you want to measure this. How much is this? That's you argue that that's in the phi direction. Here, how you would do is, algebraically speaking, you can just take the derivative. So sine phi will be minus sine phi in the I hat direction plus sine phi in the j hat direction. And what am I missing here? When I take the derivative of this, what am I missing? More explicitly on your physics. So d by dt of cosine phi I hat plus sine phi j hat. That's equal to a times minus sine phi. What am I missing? Let some space here. Time derivative, right? I have to take the time derivative of phi. I will use this chain rule, I have to complete this, that's d phi by dt. And that's d phi by dt, and d phi by dt, or usually in physics, you say the angular speed, like that's omega. So that's equal to omega times a, and this quantity that is remaining, that's phi hat, sine phi times cosine phi. That will be here, I think we do this here. So sine phi is this component here, and cosine phi is the y component. It's in the second quadrant, but comes with a negative sign. This should be very familiar here. Because it's tangent along the tangent vector, that's what we are seeing here. But here there is no time dependence, so it is just a geometric, it's a phi dependent quantity, derivative of phi with respect, derivative of the radial vector with respect to phi is the tangent vector. Quiz again, what is the derivative of phi hat with respect to phi? Any answers, immediate answers? What's the change in velocity with respect when you're going in a circle? Acceleration, what's the direction of acceleration when you're going in a circle? Radially inward, right? Good, radially inward. So it should give you the centripetal acceleration. So it should be in the radially inward, so it should be negative rho hat. Right, so you should be able to explicitly, in the quiz, you know, show that this is explicitly negative rho hat here. Show me that, that's important. Okay. All that is the connection. So we have this is equal to phi hat, and what else do I need? And d by dz of rho hat. What is that? That should be straightforward. 0, right? That's in a plane, nothing changes. So 0. If I use these quantities, I can calculate a1, 2. This is equal to rho hat times 0 plus phi hat over rho times and then there's a rho, there is a d by d phi of rho hat, that's phi hat. And plus 0 plus v hat times 0. And then you take the dot product of this. I think this is a then we will do this. This is dotted with phi hat dotted with. This is equal to, this is 0, forget about that. What we have there is phi hat over rho. That's 1, that's phi hat rho squared. So what this means is that how does my basis vector 1 change with position? Its component in the second direction is not 0. So that is a direction component in phi hat. If I take another derivative here, I say first change is usually, if you think of electricity and magnetism, that's a potential. If I take one more, that becomes a Laplacian. If I take the dot product, and that's what the curvature is. The derivative of this connection will be what the curvature is, and most of the physics typically deals with curvature. We talk about the Laplacian of the electric potential is equal to the source. In gravity, you will say that the Laplacian of the metric will be equal to the energy momentum tensor. We won't be talking about that, but this is the next step here, so that you take the gradient again, and that will give you the curvature. And you can talk about a Berry curvature or a Riemann curvature, there are different curvatures you can but I'll stop here, and we'll keep proceeding with it. I want to do some quantum mechanics, at least give some very superficial ideas of ideas in quantum mechanics using this basic vector, and then go into either complex numbers or range functions. Niranjan,
No,
are you familiar with some of this, right?
there are a lot of things going on.
Yeah, I actually agree. Yeah.
So
Any questions as such?
no.
Comments?
Probably feel like looking at the homework also.
Oh, yeah, that homework was long, right?
Right.
But you have to do only two problems, at least for the students. They have to do only two problems, and it's guided kind of, so I take them through the steps.
Okay.
So that's the same comment for you, I mean, it is. Don't be overwhelmed with the length of it's like a textbook, to kind of work out all the problems, and each step is kind of simple.
Right.
But try to get a full picture, imagine that this question was not with the so many steps. It only tells derive this, and then that's the way you want to have an overview of what it is.
Yeah. In order to understand the concept, that's what I thought. Like if I can take a look in the homework also, that will be very helpful. Yeah. I will make time for that.
Yeah.
Thank you, Dr. Sajes. Then see you
Okay,
next time.
yeah, thanks. Niranjan. Yeah. Oh, Nathan?